For centuries, men believed that a motionless, enormous Earth was the center. Now we know that our tiny Earth spins on an endless journey through a universe vast beyond our comprehension. The greatest of all telescopes has a range which is about 2 billion times the distance that light travels in a year. It puts us into a visual bubble in space which has a diameter of about 4 billion light years. Now, a light year is not a measure of time, it's a measure of distance. It is the distance that light travels in 1 year at the rate of 186,000 miles every second of that year. That is the part of the universe that we can see, that we know. Now, in photographs taken with this tremendous telescope, using the telescope as the eyepiece of a camera, exposed for hours so that we can reach out to the very end of this telescope's range, we can see some very strange things. Here is one of those pictures. Notice in it that there are some objects which are obviously not stars, little wispy ghosts of light right at the edge of this bubble in space that we know of, little spindle-shaped affairs. Do you see them there? Actually, there are about 300 of those strange objects in these pictures. Now, these are not stars. These are galaxies, really vast organizations of stars and dust and gas. And here, for contrast, is a galaxy which is rather near to us and in which we can see in some detail. We can see the complicated structure, the arms, the nucleus, and the arrangement of this galaxy. This one we can see head-on, as it were. Here is another one which is at a different angle. This one is taken edge-on, and it gives us a view of the general construction of these galaxies, a disc-shaped affair of stars and dust and gas. These things are tremendous and are made tiny only by distance. We live in a galaxy. All the stars that we can see belong to our own local Milky Way galaxy. And in this bubble of space that the telescope brings to us, we can see enough galaxies so that we have a pretty good idea of the average galaxy. Now, here is a model of a normal average galaxy. As you can see, it is roughly circular in cross-section. It has a diameter of about 100,000 light years. It has a stellar population of at least 100 billion stars. There is a vast quantity of dust and gas in between the stars, enough dust and gas to make up about 10% of the mass of the entire galaxy. And this dust and gas is concentrated largely in the outer regions of the galaxy, where we see the arm formation, which seems to be normal in the majority of the galaxies. These arms trail backward against the direction of rotation of a galaxy. This one, for example, is rotating in this direction. And in the center is a nucleus, a hub, the brightest part of the galaxy, with rather less of the dust and gas there. We see these at all angles. Some of them we see face on, as it were, from either the top or the bottom, depending upon your point of view. Others are at an angle which makes them look elliptical or oval to us. And still others we see edge-on, so that they look as that picture did, which we just saw a little while back. Now, there are a great many of these, and they all seem to have a general family resemblance. And as is the case with mankind, he has a propensity to try to classify things, to put them into little pigeonholes where he's got a lot of them which have a general resemblance together, which fall into classes. And that has been done rather successfully with the galaxies. One of the greatest astronomers, Edwin Hubble, classified galaxies. He put them into 4 general groups. The first one he called the elliptical galaxies, which had little or no arm structure and were in varying degrees of circularity, the most circular down to those which were elliptical either because of the angle at which they were tilted from us or elliptical in fact. It were elliptical in shape. In Hubble's second group, we have the normal armed spiral galaxies. And again, they were classified according to the preponderance of arm structure. In his third group, there were galaxies which seemed to have a bar rather than a circular or an oval nucleus. And the arms came out from the edge of the bar. The fourth class, which isn't shown here, was really not a class at all. Into it was thrown every galaxy which didn't conform. There are a few, a rather small group, which have no standard of shape. Now, Hubble classified these again, in each group according to their shape. In the ellipticals, the more nearly circular ones were this first group. Then the other classes were more oval or more elliptical. In the arm spirals, the classification was according to arms. Those with the least prominent arm structure were in his first classification. And as the arm structure became more prominent, they were put in different class. So were the barred spirals. Those with the least arm structure were in the first class, and an increasing amount of arm structure put them into a subsequent higher group. Now here are some wonderful pictures of these various galaxies, close enough to us so that we can see perhaps the various kinds. Here is one, for example, which has a preponderance of arm structure with a very small nucleus, and the arms are scattered and irregular. Here is one of the classics of astronomical photography. It shows a normal armed spiral face on, as it were. We can see the arms, the rotation of them. This one is moving around this way, clockwise, as you look at it on your screen. It, too, has a very condensed nucleus and a rather widespread arm structure. Here is a picture of one taken edge on. If it has arm structure, it isn't apparent to us because the arms lie in our line of sight. But we can see the disk formation with the rather deeper nucleus and the concentrated brightness in there where the stars are. This fourth picture is not a galaxy. This is a nebula, and we put it in here by contrast. The galaxies were called spiral nebulae when they were first discovered. This is a real nebula, an amorphous cloud of gas within our own galaxy, part of our own household, as it were. This is the great nebula in Orion. Now, we live in a galaxy, and the galaxy we live in, we believe, is a normal spiral galaxy, not barred, a spiral galaxy with two definite arms, and it is a little bit larger than the average. Now, this average galaxy, we believe, looks very much like ours, except that ours is slightly bigger, has perhaps a slightly larger than average stellar population. There is one very bright galaxy quite near to us. Bright enough, in fact, so that we can see it without a telescope under favorable conditions, and that is the great galaxy in Andromeda. We believe that our galaxy resembles this one very closely in form, in shape, but is only about 2/3 of the size of the Andromeda galaxy. Here is a picture of the Andromeda galaxy. It is actually circular in cross-section. Its shape, as we see it, is due to the fact that it's tilted away from us. It has a definite arm structure, two great arm portions. It has a very condensed, bright nucleus. It is perhaps 150,000 light years in diameter and has a population of somewhere between 200 billion and 300 billion stars. This, as I said, is one that we believe looks very much like ours, although it is larger than our galaxy. Now, the Andromeda galaxy and all the other spiral galaxies lie outside of our galaxy in what is called intergalactic space, in space between the galaxies. Now, here's a diagram which shows, let us say, our own galaxy, looking something like this, a normal armed galaxy. Our position in that galaxy is about 1/3 of the way in from one edge toward the center, where our sun is one of the billions of stars, and a rather small star at that. And of course, about our sun are clustered its family of planets, on one of which we live. Now, contrast this picture with the picture man originally had of the universe, where an enormous Earth was the center of everything. Now, man, through his own ingenuity, has lessened his important position a little bit and finds that he belongs on an appendage of a rather average star in a slightly larger than average galaxy in a terrific bubble of space inhabited by countless billions of other galaxies. Now, our galaxy belongs to what we call the local group. That is a group of galaxies within a fairly small space range, relatively small, rather. Here's a diagram of our local group showing our galaxy and, among others, its two nearest neighbors, the Magellanic Clouds. Now, these clouds are fairly bright, and you can see them easily if you're far enough south on the Earth. They lie in the southern sky and were first reported to civilization by the crew of that ship of Magellan's, which made the historic first voyage around the Earth more than 400 years ago. Here's a photograph of the larger of the two clouds, the large Magellanic Clouds. Now, this is an irregular galaxy. You see it doesn't take on any elliptical or spiral form. It's an irregular galaxy, an irregular little cloud of stars. This is about 200,000 light years away. Now, just stop and think of that a minute. If this thing had been destroyed in some overwhelming celestial catastrophe 100,000 years ago, we'd still be seeing it. We'd still be looking at the light which left it before then. We wouldn't know of this destruction for another 100,000 years. This one, as I say, and its little companion are the two members of the local group of galaxies to which our own galaxy, our own Milky Way galaxy, belongs. Here it is. Here is our galaxy, and here are the two Magellanic Clouds. Now, so situated that we can see them in the southern skies are three or four more small elliptical galaxies, really rather small galaxies. And in the northern part of our sky, there are two more rather small ones. Now, within the total distance of about 3 million light years is the rest of the local group, several small ones, and dominated by the great Andromeda galaxy, which is the largest one of the lot. This is our local group. This is the group of galaxies to which ours belongs. Now, that Andromeda galaxy, again, as I say, dominates this local group. It can be seen without a telescope, the most distant object that the human eye can see. You can find it on a clear, sparkling, dark fall night if you know where to look for it. You don't see anything like this tremendous photograph, however. But notice in this picture of it again that the streaking in the arms, the dark places, now those are not gaps in the galaxy. Those dark spots are caused by obscuring matter, dust which overlies the pattern of stars behind it. And we find that dust in many of the galaxies. We can see it in the arm pattern. Now, here is a photograph of a normal armed spiral galaxy. See the arms, the small nucleus, the rather widespread arms, and notice again the streaking in dark places which are caused by that obscuring cosmic dust. Now, it occurs in varying quantities. Here is another photograph which shows a galaxy, an elliptical galaxy, with a much less quantity of dust, still some traces of arm structure you see here, but you can see dust in there too, but not nearly to the extent that we saw it in the first picture and in the Andromeda galaxy, nor is there as much dust in this one as there is in our own. We know that there is a great quantity of this cosmic dust in our galaxy. And the patterns that it makes in the clouds that it forms in the sky are intensely interesting and make some of the most beautiful objects that we can see. Here is one of the very famous clouds of cosmic dust. This is the Horsehead Nebula, again in the constellation of Orion. In the imagination of the man who discovered this, it did perhaps look like a horse with its arched neck and head looking out of the barn door. But it actually is a vast cloud of dust. You can see the edge of that cloud going across here. This is a bay protruding from that edge. Notice how many more stars and how much more light is visible out here to the right beyond the edge of the cloud than over here. Here we can see a few isolated stars. And just stop and think now the size of this cloud. These isolated stars, let's say that they're average stars, like our sun, about 1 million miles in diameter. This is enormous. There's a lot of dust up there. Another very famous such cloud lies in the southern skies, in the constellation of the Southern Cross, and is called the Coal Sack. Now, here's a picture of that. Here's the Southern Cross, the smallest constellation in the sky, incidentally, and these 4 stars make the cross. And just below it is the Coal Sack, that vast dark region caused by dust accumulated and overlying the stars. Now, in many a galaxy, we can see this dust. Look at this one, for example, that we saw before. This galaxy seen edge on. See that dark line through it? Makes it look like a sandwich of light with a dark filling. That's dust, scattered and concentrated in the edges, the disk of the galaxy. That is where most of the dust lies. Now, we find, as I told you, we find dust in varying amounts in the galaxies. And we're going to look at a picture now of a galaxy which has very little dust in it. It's quite clean. This is this one. Do you see how nearly circular it is? How reduced and how insignificant the arm structure is. And we can just make out perhaps just a modicum of dust in there. Now, this is very interesting. It gives us a great range of differentiation, and it has led to some quite interesting speculation. As is man's habit, as I said, when he gets a number of objects, he not only tries to put them in classes, but he tries to find a beginning and an end to them, trace a theoretical process of evolution, and that has been done in the case of the galaxies. At first it was said that the elliptical galaxies, those which were circular in cross-section or slightly oval, but without any trace of arms, were the young ones. They began the thing. Then from this point, they branched out in two parallel branches. We had first those with a minimum of arm structure, more arm structure, mostly arm structure. And the same way with the barred spirals. You remember this other classification that we looked at. A minimum of arm structure, more arm structure, and a maximum of arm structure. This was supposed to be the progress of evolution of galaxies. But we have learned something in the last 30 years that may change all that. We have seen galaxies colliding, two galaxies hitting each other. Now that sounds like a terrific celestial catastrophe, but actually it isn't so bad. You see, the stars in any galaxy are so widely separated that one galaxy can pass right through another without the stars in one galaxy touching at all or affecting in any way the stars in the other galaxy. But the dust and the gas, this dark material, is blown out of each galaxy with terrific turmoil. And here is a photograph of the edge of two galaxies which are colliding. You can see that something is going on up there. This dark material is being forced out of the galaxy. Now, that makes for a little revision, perhaps, in our theoretical evolution of the stars. If the galaxies without dust have been through collisions, perhaps they should come later than they did before. You see, galaxies do collide. There are a lot of them up there, and in spite of the vast amount of space, there are enough galaxies in any one area so that at least 10 galactic collisions are going on all the time. This is in the average region of space. There are regions in which the galaxies are more crowded. And in these crowded regions, we know that a single galaxy can endure, or has endured rather, anywhere from 5 to 30 different collisions in the 5 billion years which we say is the lifetime of the universe. So, the process of evolution may be reversed. These may be the young ones, full of dust and gas, but having undergone a series of collisions, they lose that dust and gas. The arms are absorbed, and they become, and you might say, all nucleus. There is no dust. The arms are gone. These may be the old ones. We don't know that yet, but that may be the way it works. Now, here is a picture of a region of the sky in which there are a number of galaxies. Look at them. There are very few with obvious arms. Some of these which we see edgeways may have arms in our line of sight. These are clean galaxies. And in the regions of space where the galaxies do seem to be clustered, the clean galaxies predominate. They have apparently gone through a number of collisions. And we find that intergalactic space is also filled with free oxygen. Both of these things are indications that the galaxies have collided. So, you see, we may reverse our whole concept of it. Now, what have we got up to this point? Here we have a bubble in space, 4 billion light years in diameter. Now, we have no reason to believe that this is not a typical section of space, that what we see going on in here is not being repeated throughout all of the extent of space. Galaxies of all sizes, at all angles, but enough of them so that we can form an average galaxy. Remember the average galaxy? About 100,000 light years in diameter, containing at least 100 billion stars and, of course, vast quantities of dust and gas in the shape of clouds within it. Now, what are these galaxies all doing? Well, they're moving. And where are they moving? Away. Away from each other. We analyze the light from the galaxies through a spectroscope. The telltale dark lines in the spectrum, the resulting image of the light that we see, are all shifted a little bit toward the red end of that spectrum. Now, that means that these objects are moving away. That's the famous red shift, the Doppler effect, the lengthening of the waves of light by the recession of the object giving it. They're moving apart. And the most distant galaxies that we can see are moving much more rapidly than the intermediate ones, which are moving again more rapidly than those which are nearest to us. So it would seem as though everything started at one point, billions and billions of years ago, and began to move out. It seems that way. But let's stop a minute. We are looking at light, in the case of those at an extreme distance, which is 2 billion years old. Is it safe for us to assume that light then behaved in the same way as light created last year or yesterday? Or does the journey affect light? A travel through space of 2 billion years. We are looking, maybe, at fossil light or at tired light. We don't know. Astronomy must stop and ask itself these questions once in a while, just to be sure that it isn't rushing in, let us say, where angels fear to tread. Now, again, in this bubble of space, we seem to trace the framework of an organization of galaxies, a galaxy of galaxies, a flat disk-like arrangement of the galaxies, perhaps like our galaxy, except with galaxies where these are stars. Again, we are one, our galaxy, when I say we this time, of a great disk of galaxies. It looks that way. We haven't been able to definitely outline it, but the clustering, the arrangement, the distribution of these gives it that appearance. It's the old Chinese puzzle, a big box, a little box, a little box, a little box, until we get all the way down to our tiny Earth around its sun. How many galaxies are there? Well, we don't know, of course. There is an estimated 4 galaxies in our bubble of space that we know of. 4 billion average galaxies, each with a population of 100 billion stars. Think, how many stars are there in space? Sir James Jeans, the great British astronomer, perhaps has the best answer for that. He says there are as many stars in space as there are grains of sand on all the beaches of all the oceans of the world. That's the picture that astronomy has built up of its universe. A picture begun at times with intervals of hundreds of years between each new acquisition of knowledge. Astronomy has called upon other sciences, mathematics, physics, chemistry, biology, statistics, and all the rest, to supplement its own findings. And this is our picture now. Still 99% mystery. Here we are, living on a little planet around the sun, a sun which is a very average star, one of billions of stars in our galaxy, and ours is just one of billions of galaxies. Now, this is a vast organization, too vast, it seems, to have been created solely for people living on one little speck, lost in it somewhere. Is it possible that there may be other inhabited planets? Since our sun is a very common type of star, we know that there are millions of stars like our sun right in our galaxy alone. Our sun is the only star who we know of, though, that has a family of planets on one of which we live. There may be others. Even if there were planets around the nearest of stars, we would never be able to know of them visually. They'd be too close to the star and too far away. But if we only knew how our sun got its family, is that unique or is it a common experience? We believe that it is a common experience. Now, biology comes into the picture. In all our investigations of light from the most distant galaxies, we have never been able to find any trace of any except the standard classic 92 elements. There are, of course, about a dozen more which we have created through our atomic experiments. But there are no other elements. And we know, biologists tell us, that 13 of these elements, worth incidentally about $1 in the common market, combine to make the human body. And therefore, if life does exist anywhere else in the universe, it must be precisely as we know it here on Earth. We know that life requires certain standards for its existence. These are, of course, a temperature range, a very narrow temperature range, from about 40 below zero to 120 above zero. That is very narrow in a universe in which the low point is 459 below zero, and the high point are the millions of degrees that we find in the interiors of stars. Life needs oxygen. Our atmosphere on Earth has 20% oxygen in it. Life needs water. 60% of our bodies are water. Life needs energy, radiation from the sun. We get that either directly or indirectly from vegetation. We either eat the vegetation ourselves or eat animals that have fed upon it. These we need for life. It can't be found in our sun. There is only one other possibility in our solar system, and that is Mars. And if life exists upon Mars, it can only be in the form of a very primitive vegetation, such as moss or lichens. Now, our sun is a common star. There are millions like it. Let us be conservative and say that 1% of the stars in our galaxy have planetary systems. That leaves us 1 billion planetary systems. 1% of those systems have planets so situated that life is possible upon them. That is 10 million inhabited worlds in our galaxy. In our bubble of space, there are an estimated 4 billion galaxies. That gives us a possible 4 billion million inhabited worlds. Believe me, we are not alone.
This is National Educational Television.